Do you happen to know why it's called an orthogonal matrix? I can't remember why M inverse equaling the identity is relevant. Okay, so that's not quite the definition of orthogonal. The definition of orthogonal is that a matrix M is orthogonal if M transpose is orthogonal. Sorry, is the identity, excuse me. So a matrix M, which is n by n, so it's a square matrix, is orthogonal if M transpose M is equal to the identity matrix, right? So why do we apply the adjective orthogonal to M? Well, the reason is because it turns out that theorem, this is really easy to prove. If M is orthogonal, then the columns of M are orthonormal. So what does orthonormal mean? It means that the dot product of the ith column and jth column is equal to what's called the delta ij. Sometimes written like maybe like this. Well, we'll write it like this, okay? Delta ij. What the hell is delta ij, you ask? It's sometimes called the Kronecker delta. No idea why, but that's what it's called. And it's 0. It's very simple. It's 0 if I is not equal to j, and it's 1 if I is equal to j. So this is really just a handy notational device. Don't get intimidated by it. But let's think about what this is saying. So if M is orthogonal, and actually this is an if and only if. This is an if and only if. M is orthogonal if and only if the columns of M are orthonormal. So what this is sort of saying is, you know, if you interpret the dot product geometrically, which you should, what this is sort of saying is that the columns of M, any two different ones, always make a right angle with each other. That's what the 0 bit is about. The fact that when we take the dot product of two of them, those vectors are make a 90-degree angle. The other part of it is that each of those vectors is of unit length, right? So it's like the columns of M kind of look like the standard basis for Rn, right? With a 1, like 1 0 0 0 0 0 blah blah blah, 0 1 0 0 0 0 0 0 1. You know the standard basis, I hope, for Rn. So that basis is really lovely to work with, right? Because all of the vectors are orthogonal to each other and they're all of unit length. Such a basis is called an orthonormal basis. And so orthogonal matrices have this property that their columns are orthogonal. Sorry, their columns are orthonormal, but we call the matrix orthogonal. It's a disconnect in words. Probably a better word, if we could revise history, we would say that M is orthonormal as a matrix. But the ship has sailed. We must live with these inadequacies. But that's what it means. So how can you prove this fact? It's actually incredibly easy to prove. Because if you think about what M transpose M looks like, so M transpose M, if we think about M as if we think of M as being consisting of columns C1, C2, all the way up to Cn, then what does M transpose M kind of look like? Well, we're going to take so if we transpose this, it it's like we're taking C1 and then we're transposing that vector, right? So this right now, this C1 is a column vector with n entries in it. So when we transpose M, that first column becomes the first row. And that first row is C1 transpose. Hopefully that makes sense. And we keep going like this all the way down to Cn transpose. That's M transpose. I should denote, label this. This right here is M transpose. And then we're multiplying this by M, which of course is this guy. So that when we take the product, right, what we're doing in every entry here, so like this entry right here, the 1, 1 entry, well, that's going to be C1 transpose times C1. So this is C1 transpose times C1. And if you think about what that is, well, that's the dot product of C1 with itself. What will the 1, 2 entry be? That will be C1 transpose with C2. What is that? That's the dot product of C1 with C2. And you can keep going like this, of course. The ijth entry is the dot product of Ci with Cj. And if you look at this definition, right? Or sorry, yeah, if you look at this Kronecker delta here, you'll see that this is exactly describing the entries of the identity matrix, right? 1's down the diagonal when I is equal to j, and 0's off diagonal. Yeah, it's cool, huh? Yeah, I agree. Anyway, hopefully that makes some sense. And of course, this is, yeah, that's the way to think of it. Of course, anytime. Good question, Decodius. I have a question about Lagrange multipliers. I've seen them in 2 different forms, but I can't quite get how they're equivalent. Honestly, I can barely conjure one of the forms, but I certainly am not sure exactly what it is that you are speaking of. So maybe you can enlighten me. Do I do personal mentoring off stream? Is it possible to private message me for help somewhere? Sure. I have a Discord that you can join. If you DM me there, I can probably help you out. Sorry, I can probably respond there. I don't know if I can help you. Don't know. Could I recommend a book to go into fundamental linear algebra and calculus? Well, here's a book that I know I will never recommend to you. Don't ever buy the manga guide to linear algebra. It's toxic. Fundamental linear algebra. So when you say fundamental linear algebra, do you mean like like what do you mean? Are you wanting to go on into further into math or physics, or are you more of a like an engineering track, maybe computer science? What kind, like, depending on your future studies, you might get more or less benefit from various types of textbooks, because various books might emphasize more like abstract ideas versus more concrete ideas, applicable ideas, in the sense of being like applicable in the real world. You do what you need to do. I'm fine. I'm fine letting them know that I found their work abysmal. Yeah. You want to reinforce your knowledge in math. I'm an informatic engineer. Yeah, so linear algebra for math people is like a language, and it's really framed around things like you don't need to buy it. You can find it online. It's really framed around things like vector spaces and linear transformations between them. Do I know a book? So the way that I picked that stuff up, I guess, was mostly through like abstract algebra textbooks, probably. And also like just sort of like trying to understand what the hell was happening in my undergraduate linear algebra class, in my lower division linear algebra class, that sort of thing too. Let's see. What then is a good recommendation? So a lot of people seem to like Axler's linear algebra done right. I think that there are some channel users in here that might have read the book and have had good things to say about it. So maybe that book, Axler's Linear Algebra Done Right, is a good place to go. Oh, you have that book. Yeah, it seems like a lot of people seem to like it. So that seems like a fine endorsement. So you know what? By proxy, I will endorse it as well, because I trust these people that are saying that it's good. I would have studied physics. No, sorry, not game development. I've never really had a keen interest in, like a super keen interest in computer programming. That's changing a little bit more now that I'm hearing about a lot of stuff around like machine learning and stuff and data-driven programming. It seems interesting to me. But like, and I love the power that programming gives you. So like, actually, frankly, like for my own children, I have two small boys, 8 and 11. Like, the number one skill that I want them to have before they go to college and as they enter into adulthood is to be able to program a computer. I think it's incredibly important. So I do understand, like, I know how to use Python, not well. If anybody looked at my Python code, they'd make fun of me. But I can do it well enough, with the assistance of the internet, of course, to sort of get by and do the things that I want and need to do. So I like that. I really enjoy the power that comes with that. But like intrinsically, it's never really been a source of fascination for me, I guess. But full respect to everybody that does do that kind of stuff and is into it. The other thing that was super interesting to me, the two things that were super interesting to me coming out of coming out of high school, were math and physics. And and I've told the story a lot. I have physics envy now, but back then the problem was I had to do labs. And I didn't like labs because I don't like holding a stopwatch and I don't like sig figs. Serge Lang's linear algebra book. I'm not familiar with that one. What I'm familiar with is his yellow book on algebra. Well, no, I'm not even familiar with that. I just remember people carrying it around, which is not familiarity at all. Okay, that's nothing. You think people that study math and then do a CS major are monsters? Good monsters. Oh yeah, I have a question queue. So if you have a question, you can type !join. Oh, and also in news, I uploaded a video of the stream 2 days ago, an edited version of that stream. On that stream, we talked about things as diverse as... Oh, we talked about Gaub, one of the greatest mathematicians of all time. We also talked about singular homology. We talked about isomorphisms, group isomorphisms. And we also talked about why it's a good idea if you are a math person to make friends, which I know is a tall order for some of you fuckers. I've been there. Listen, I speak from experience, okay? So you can't get all mad at me. I've been where you are now, okay? So just take it easy. Oh, and we begin our read through of the manga guide to linear algebra. Spoiler alert, 0 out of 10. Toxic text that. I can't believe we give this to children. Texture13, thank you for following. I'll upload yesterday's stream in which we finish our reading of the manga guide to linear algebra. That will go on the YouTube tomorrow. Tomorrow, yeah. Because CalcMath says I have to do one YouTube video every day. And then that's what CalcMath said. And I trust CalcMath. There's also a manga guide to calculus. Now, I've not read it. I'm just guessing. I'm guessing it's trash. Oh my god. Trigonometric functions are incredibly important. They are among the most important functions that we have. Why is that? Okay, so you're probably learning boring stuff right now. For example, you might be learning about the sine and the cosine, and maybe you don't understand why those things are at all important or applicable to the quote-unquote real world. But all I can do is just sort of very authoritatively tell you that they are absolutely critical. What was I saying? Oh yeah, trig functions. They are incredibly important. They are among the most important functions that you'll learn. They're not just there to torture you, put it that way. So for example, yeah, you can add a question or a comment as an argument, and it shows up on my end. Let me get my dot cam up. Yeah, exactly. So, for example, like maybe you're interested in physics. Maybe. And what you'll learn in physics are about these are problems that involve basic things like cannonballs and such. So like if you have a cannon or a projectile fired from a cannon, okay? and it comes out of that cannon at with a certain velocity. So there is like a muzzle velocity or something like that, a velocity of the cannonball as it is launched out of this thing. This velocity you're going to represent using what's called a vector. Don't be scared. A vector is just a dumb arrow. Okay, it is an arrow that has a certain length and it has a certain direction. That's all a vector is. Okay, in mathematics, it also means disease carrier in many other contexts, like whatever. Oh yeah, did you know there's a pandemic outside right now? Anyway, just to remind you. So V. So you are going to be keen on, for example, decomposing this vector. What do I mean by that? I mean, in the future, not so distant future, if you take physics, what you're going to do with this V is you're going to write it as a sum of a component that is in the purely horizontal direction and a component which is in the vertical direction. Because it turns out that those directions, physically speaking, are in some sense independent of one another. And you can understand the total flight path of the cannonball if you understand these two vectors, if you can figure out what these two vectors are. Now, I insist, I'm right, that what you are going to need to do in order to get this decomposition, that just means breaking the vector V down into pieces. What you're going to need to do is you're going to need to understand trigonometry, because you're going to want to know this angle here. If you were to call it theta, then it will turn out that this vector here, well, you can figure out sort of what its length is. The length of this vector pointing in the horizontal direction is going to be equal to the norm of the length of this vector. So we denote that with vertical bars like this. This is sometimes pronounced the magnitude of V, aka also the norm of V. Don't be scared, these are just stupid words. Multiplied by, I don't know if you guessed it or not, cosine theta. Cosine theta. That's like really what this vector is. And you need to know that if you want to know how far horizontally this cannonball is going to move, or gonna fly before it hits the ground, assuming the ground is level. Similarly, this vertical vector here, you can figure out what its length is by doing norm V sine theta. All right? So that's just one application. Another application. You know all those like you've listened to music on the internet before, right? So there are these very, very tiny files called MP3 files. I don't know, or maybe, I don't know, do kids even know about MP3 files these days? Anyway, music can be compressed into tiny files. Tiny, small-sized files. So like you can get like a 4-minute song in a 4 megabyte file. It's absurd. How is that done? Well, it's done through some fancy sampling processes, and it exploits something called Fourier Theory. Yeah? Fourier Theory, where you can take a complicated analog sound signal, which might look like, you know, some complicated, crazy thing like this. And what you can do is, again, you can decompose it. You can break it into pieces, which turn out to be that the great pieces to use to decompose a sound wave like this are sines and cosines. Express this as a sum of sines and cosines. It's incredible. This decomposition is called Fourier Analysis. Fourier is some French guy who did work in this. Okay, if that's not convincing enough, you should understand that it seems as though sines and cosines they're just baked into reality. Maybe these things aren't enough. I don't know. But they are baked into reality. And our best theories of reality, I'm talking about like quantum field theory and things like that, we need sines and cosines. They're not optional. They are absolute musts. So hopefully that feels good. Pepe Storm is next. I listen. I've said 3 things. There's probably 3 trillion things that one could say. Don't forget about trigonometry. No, don't do that. Oh, I don't know anything about machine learning. I'm sorry. Maybe Strang's linear algebra book, because he seems like a guy that is like for example, I know that like the singular value decomposition is probably the most important for applied math, the most important matrix factorization. And I'm just going to go out on a limb. And it is a bit of a limb. I don't know, because I'm really not familiar with machine learning. But I'm going to guess that the singular value decomposition is of absolutely incredible use in machine learning. So maybe look at Gilbert Strang's linear algebra book. He's a dude at MIT, and he also has a linear algebra course online. He's actually pretty entertaining to watch because he seems like a really nice guy. Oh yeah, see, okay, great, perfect. Yeah, linear algebra. Strang made a new book in 2019 called Linear Algebra and Learning from Data. I skimmed through it, and it was mostly linear algebra, but completely relevant to learning from data/ML. I am super intrigued by the whole machine learning thing. Like, it seems like, first of all, I was like, is this real or is this just a fad? I don't think it's a fad anymore. I mean, I felt this way for a while, but at first, buzzwords come out. It's like blockchain. It's like, okay, let's see what comes of it. But it seems like machine learning really is like a new paradigm. The one that I don't recommend is the Manga Guide to Linear Algebra. Okay, you're not going to get anything good out of that. So that's hopefully a good answer for you, Pepe Storm. If AB is equal to BC, if AB is equal to AC, why can't we assume B is equal to C? So are we talking in the context of like rings? So, well, first of all, AB equals AC. So does this really imply in any situation, actually? Does this, like, even over the real numbers or integers, it doesn't matter. Is this really a true implication? I claim it's not. I think there is a problem here. So the problem is, what if A is 0? If A is 0, then it doesn't matter what B and C are. Then because 0 is equal to 0, but that does not necessarily mean that B is equal to C. So this is a problem. The problem, of course, is that you can't divide both sides of this equation by 0. Dividing by 0, as you know, is the cardinal sin of arithmetic. Now, you can extend this to rings more broadly by talking about these things called zero divisors. But if you don't know what rings are, don't worry about it. Okay. So hopefully, do you feel satisfaction, Iconic? Could you explain me integrals by definition? Like, I used to do the definition to make the derivative, but I cannot understand the same concept in integrals. Hope it's not a dumb question. Definitely not a dumb question. It's not a dumb question either. It's a hot question. So really, I imagine that where you're at right now is in calculus. That's what I imagine you're at. Is Senko Moon still in here? Like, am I talking to nobody? I don't want to say this if nobody's gonna get anything out of it. Senko Moon, are you out there? All right, I guess I'll do it. Well, no, maybe I shouldn't. Let's see. Where did my Streamlabs go? One sec. Yeah, go. Nyarlathotep Smith. What's your question? It's you. Hi. Good to see you again. I'd remember that name anywhere. Why is... Oh, God. The ext functor. I'm going to have to say that I don't remember enough about it. Ext and tor. I've forgotten both of those. So I'm going to have to plead. I'm going to have to say I don't know. I definitely learned it at some point in my life, but it's fallen out of my brain. Does anybody else in the chat perhaps know about ext? This is good. I mean, it's not good for you because it's total. I'm being totally worthless here. I've wasted your time. But it's good because I should probably know that. It's a basic part of algebraic topology. But NCAT lab. We're really gonna go to NCAT lab to try to learn something about ext and tor. No, where I remember reading it was Hatcher. I think that ext and tor pop up in the context of the universal coefficient theorem. Which is sort of like, why can't cohomology just be easy? Why can't cohomology just be hom of homology? So, but I really can't remember sort of how that chain works. The chain of logic there works. Like, there is a map of the cohomology group into hom h sub I. Like there is a map I think that goes from the ith homology group with some coefficients in I don't know, with coefficients somewhere r into hom of the ith homology group into R or something like that. But, and I think that this map like the dream. This is like the freshman's. This is the freshman's. This is the equivalent of the freshman's dream that x plus y squared equals x squared plus y squared. The dream is that this is an isomorphism, but it's not in general. And I think that these ext and tor fuckers are the things that get in the way. But I can't. Yeah, I can't remember the thread. How that works. What's going on? Have I seen the map of mathematics? Nope. I remember back in the, there used to be this guy, Rusin, who used to have a math site. And he had an atlas of mathematics. I remember that. The Mathematical Atlas. Does that guy still exist? Dave Rusin, I believe was his name. And I looked at his map of mathematics, or his atlas of mathematics, quite a bit. This was in the early days of the internet, 95. Some of you weren't even born. Many of you were not born. Does it still exist? Curious. Dave Rusin. Math Atlas? I think that's what it was called. The Mathematical Atlas. There it is. Yes! I used to yes. I used to look at this all the time. I don't know why. This image. Yes.
The mathematics we learn in school doesn't quite do the field of mathematics justice. We only get a glimpse at one corner of it, but mathematics as a whole is a huge and wonderfully diverse subject. My aim with this video is to show you all of that amazing stuff. We'll start back at the very beginning. The origin of mathematics lies in counting. In fact, counting is not just a human trait. Other animals are able to count as well. And evidence for human counting goes back to prehistoric times, with check marks made in bones. There were several innovations over the years, with the Egyptians having the first equation, the ancient Greeks making strides in many areas like geometry and numerology, and negative...
If I could fucking draw. If I could fucking draw, I feel like I'd, you could destroy YouTube. Look at this. But I can't draw. These are so cute little drawings. I can't do any of that.
Zero as a number was first used in India. Then, in the golden age of Islam, Persian mathematicians made further strides and the first book on algebra was written. Then mathematics boomed in the Renaissance along with the sciences. Now there's a lot more to the history of mathematics than what I've just said, but I'm going to jump to the modern age and mathematics as we know it now. Modern mathematics can broadly be broken down into two areas: pure maths, the study of mathematics for its own sake, and applied maths, when you develop mathematics to help solve some real-world problems. But there's a lot of crossover. In fact, many times in history, someone's gone off into the mathematical wilderness, motivated purely by curiosity and kind of guided by a sense of aesthetics. And then they've created a whole bunch of new mathematics, which is nice and interesting, but it doesn't really do anything useful. But then, say, 100 years later, someone will be working on some problem at the cutting edge of physics or computer science, and they'll discover that this old theory in pure math is exactly what they need to solve their real-world problems, which is amazing.
Okay, so, first of all, this origin story about complex numbers, I don't know if that's historically accurate. Like, somebody was just sort of playing around or something like that. Like, it arose out of a real need to solve cubic polynomials. Like, people were fine for a while rejecting complex numbers when they arose in the context of quadratic equations, because they could just very easily say there's no solutions, right? But what they found is that when they were goofing about with cubic polynomials, they found that they absolutely needed complex numbers to be able to compute the real root to a cubic polynomial. This story is in Visual Complex Analysis, that textbook that I am in love with. So like, it's not quite that somebody just sort of thought of complex numbers whole hog out of their brain and was like messing around and then figured out that they were beautiful and useful. It's more like they arose out of necessity or an application.
And this kind of thing has happened so many times over the last few centuries. It's interesting how often something so abstract ends up being really useful. But I should also mention that pure mathematics on its own is still a very valuable thing to do, because it can be fascinating and on its own can have a real beauty and elegance that almost becomes like art. Okay, enough of this highfalutin. Let's get into it. Pure maths is made of several sections. The study of numbers starts with the natural numbers and what you can do with them with arithmetic operations. And then it looks at other kinds of numbers, like integers, which contain negative numbers, rational numbers, like fractions, real numbers, which include numbers like pi, which go off to infinite decimal points, and then complex numbers, and a whole bunch of others. Some numbers have interesting properties, like prime numbers, or pi, or the exponential. There are also properties of these number systems. For example, even though there's an infinite amount of both integers and real numbers, there are more real numbers than integers. So some infinities are bigger than others. The study of structures is where you start taking numbers and putting them into equations in the form of variables. Algebra contains the rules of how you then manipulate these equations. Here you'll also find vectors and matrices, which are multidimensional numbers, and the rules of how they relate to each other are captured in linear algebra. Number theory studies the features of everything in the last section on numbers, like the properties of prime numbers. Combinatorics looks at the properties of certain structures, like trees, graphs, and other things that are made of discrete chunks that you can count. Group theory looks at objects that are related to each other in, well, groups. A familiar example is Rubik's Cube, which is an example of a permutation group. And order theory investigates how to arrange objects following certain rules, like how something is a larger quantity than something else. The natural numbers are an example of an ordered set of objects, but anything with any two-way relationship can be ordered. Another part of pure mathematics looks at shapes and how they behave in spaces. The origin is in geometry, which includes Pythagoras, and is close to trigonometry, which I'm sure we're all familiar with from school. Also, there are fun things like fractal geometry, which are mathematical patterns which are scale invariant, which means you can zoom into them forever, and they always look kind of the same. Topology looks at different properties of spaces where you're allowed to continuously deform them but not tear or glue them. For example, a Mobius strip has only one surface and one edge, whatever you do to it. And coffee cups and donuts are the same thing, topologically speaking. Measure theory is a way to assign values to spaces or sets, tying together numbers and spaces. And finally, differential geometry looks at the properties of shapes on curved surfaces. For example, triangles have got different angles on a curved surface. And brings us to the next section, which is changes. The study of changes contains calculus, which involves integrals and differentials, which looks at the area spanned out by functions or the behavior of gradients of functions. And vector calculus looks at the same thing but for vectors. Here we also find a bunch of other areas, like dynamical systems, which looks at systems that evolve in time from one state to another, like fluid flows or things with feedback loops, like ecosystems. And chaos theory, which studies dynamical systems that are very sensitive to initial conditions. Finally, complex analysis looks at the properties of functions with complex numbers.
How is that complex analysis?
At this point, it's probably worth mentioning that everything
that
here
picture
is a lot more
was
interrelated than I've drawn. In reality, this
you just get look at this is the picture of complex analysis. Does this evoke complex analysis to any of you? If I was to cover up the word complex analysis, would you guess that this was complex analysis?
should look more like a web tying together all the different subjects, but you can only do so much on a two-dimensional plane, so I've laid them out as best I can. Okay, we'll start with physics, which uses just about everything on the left-hand side to some degree. Mathematical and theoretical physics has a very close relationship with pure maths. Mathematics is also used in the other natural sciences, with mathematical chemistry and biomathematics, which look at loads of stuff from modelling
mathematical chemistry? I've actually never heard of that in my life.
Molecules to evolutionary biology. Mathematics is also used extensively in engineering. Building things has taken a lot of maths since the Egyptians and Babylonian times. Very complex electrical systems like aeroplanes or the power grid use methods in dynamic...
Aeroplanes. Did you hear that? Aeroplanes? God.
...systems called control theory. Numerical analysis is a mathematical tool commonly used in places where mathematics becomes too complex to solve completely. So instead you use lots of simple approximations and combine them all together to get a good approximate answers. For example, if you put a circle inside a square, throw darts at it, and then compare the number of darts in the circle and the square portions, you can approximate the value of pi. But in the real world, numerical analysis is done on huge computers. Game theory looks at what the best choices are given a set of rules and rational players, and it's used in economics when the players can be intelligent, but not always, and other areas like psychology and biology. Probability is the study of random events like coin tosses or dice or humans, and statistics is the study of large collections of random processes, or the
probability is pure math, right?
organization and analysis of data. This is obviously related to mathematical finance, where you want to model financial systems and get an edge to win all those fat stacks. Related to this is optimization, where you're trying to calculate the best choice amongst a set of many different options or constraints, which you normally visualize as trying to find the highest or lowest point of a function. Optimization problems are second nature to us humans, and we do them all the time, trying to get the best value for money or trying to maximize our happiness in some way. Another area that's very deeply related to pure mathematics is computer science, and the rules of computer science were actually derived in pure maths.
Computer science is just applied math, people.
Computers were built. Machine learning, the creation of intelligent computer systems, uses many areas in mathematics like linear algebra, optimization, dynamical systems, and probability. And finally, the theory of cryptography is very important to computation and uses a lot of pure maths like combinatorics and number theory. So that covers the main sections of pure and applied mathematics, but I can't end without looking at the foundations of mathematics. This area tries to work out the properties of mathematics itself and asks what the basis of all the rules of mathematics is. Is there a complete set of fundamental rules, called axioms, which all of mathematics comes from, and can we prove that it's all consistent with itself? Mathematical logic, set theory, and category theory try to answer this, and a famous result in mathematical logic are Gödel's incompleteness theorems, which, for most people, means that mathematics does not have a complete and consistent set of axioms, which means that it's all kind of made up by us humans. Which is weird, seeing as mathematics explains so much stuff in the universe so well. Why would a thing made up by humans be able to do that? That is a deep mystery right there. We also have the theory of computation, which looks at different models of computing and how efficiently they can solve problems, and contains complexity theory, which looks at what is and isn't computable, and how much memory and time you would need, which, for most interesting problems, is an insane amount. So that is the map of mathematics. Now, the thing I've loved most about learning maths is that feeling you get where something that seems so confusing finally clicks in your brain, and everything makes sense, like an epiphany moment, kind of like seeing through the Matrix. In fact, some of my most satisfying intellectual moments have been understanding some part of mathematics and then feeling like I had a glimpse at the fundamental nature of the universe in all of its symmetrical wonder. It's great. I love it. Making a map of mathematics was the most popular request I got, which I was really happy about because I love maths and it was great to see so much interest in it. So I hope you enjoyed it. Obviously, there's only so much I can get into this time frame, but hopefully I've done the subject justice and you found it useful. So there'll be more videos coming from me soon. Here's all the regular things, and it was my pleasure. See you next time.
All right. What do I think? I thought it was okay. But I do have some criticisms. All right. I think the main thing is that this idea that these things are cordoned off in that way, I don't think that's a healthy way of thinking about math. Like, the coolest, oftentimes you get really awesome, cool math that happens when bridges between what seem like very distinct fields are constructed. So, for example, you might have topology, a very wide-ranging set of questions in that field, but what you can do, I'm not sure why I'm saying that, but you have topology, okay, which is its own thing for sure, and then you have like group theory over here, which is its own thing, or algebra, whatever you want to call it. You can build a bridge between them, and it's called algebraic topology. And I'm not saying that he's not well, what I'm saying is that this map suggests that there really isn't all that much connection between those things. At least those connections are not made explicit. Not that that needs to happen, but just having an awareness that's oftentimes what's super cool is when these bridges can be built between fields, I think is something that's sort of not in this map. Obviously, they can't really be, he can't really be totally comprehensive with his map either. Certainly there were big, huge things that were sort of missed that I think anybody would call mathematics. Almost anybody would call, for example, like, it's pretty widely accepted at this point now, algebraic geometry really is math. And it wasn't in there. So anyway, there's that. But I mean, I thought it was pretty good. It's good for, like, probably good enough for most lay people to sort of get a picture of what mathematics is about, I can see that. And the organization was kind of nice. Yeah, was combinatorics there? I'm not sure. I think it was, right? Graph theory, yeah. Graph theory, he put it here. Graph theory and or is that just graph theory? Combinatorics, there it is. Well, it starts out as solutions to polynomials, and then it morphs into some goddamn monstrosity. I mean, sorry, a beautiful landscape.
With any two-way relationship.
And I don't know. It's hard. Yeah, I don't have enough. I cannot claim to be an expert in algebraic geometry enough to know how to describe it in simple terms. Well, you know what? I will say that early when I was learning about category theory, it was hard for me to understand why it was there. I understand that much more now, so I don't have the same perspective. But when I first started learning about category theory, it's kind of like, well, what is the new thing, the new insight that this gets me? Because I don't think I really understood the power of that kind of abstraction that they were doing. Like, it seemed like, okay, I know about algebra, I know about topology, I can see that these things are functors that link, topological spaces with groups. That feels like a functor. It's very functorial. It has all these beautiful properties, right? And you can see this theme playing out over and over again. So it's a hard thing to miss. And I couldn't see that what category theory was doing was something more than just pointing that out. You see what I mean? But now I'm sort of convinced that if you walk up that mountain of abstraction on a particular path, so like let's say you go up the mountain using some ideas from algebraic topology, then this is what I like to imagine. When you're climbing up that mountain, you get some distance up to the top. You can turn around on that mountain, and you can look down the mountain, and you can see the various ways in which the various paths that you didn't take up that mountain of abstraction. You can see those other paths, and you can identify them and give names to those paths in some sense, and see how those paths get you to the same point where you currently are. And maybe also those other paths, right, are things that are as of yet undiscovered. So you can use this general machine to construct new things in different fields of mathematics. I don't think I properly appreciated this process when I first learned about category theory, particularly in the context of like what I knew at the time, which was mostly algebraic topology. And like cute things like a group is a groupoid with one element, or that a group representation is a functor. It's like fun. It's fun to do that, to recast it in this abstract language, but it didn't feel productive, I guess. But now I sort of appreciate that. Smackdown crew of the center. What just? Oh my God. Am I reading this right? QST 07. Oh my God. That is so generous of you. Holy shit. You are Wow, that's incredible. Thank you so much, QSD. That really means a lot. Thanks for supporting the channel like that. That really, really means a lot. Wow. Amazing. Yeah, Galb's in chat for QST07. Galb's. Well, I have to drink bean juice? You know what? I'm going to make a batch of beans. Not right now, not this second. But I'm going to make some beans and we'll get some bean juice going, okay? I think it is. QST, you're so generous. Thank you so much. That's amazing. It's a Galb. Yeah, it's a Galb. Somebody get the screenshot. Did I? So does x mod y times a so let me see if I understand the question. Yeah, it means to the power of. So when you write x mod y to the power of a to the power of b, so this is literally what you wrote. X mod y to the power ab. So what I want to understand is what you mean precisely by this. So certainly, one way of interpreting this is that we're taking the equivalence class of x mod y, and we're going to raise that to the 8th power, to the power a. So we're going to multiply it against itself a times. And that's a well-defined thing that gives you some equivalence class mod a. And you can do that, yeah. So in other words, I think that the answer to this question is yes. What both of these things represent are the equivalence class of x mod y multiplied by itself ab times a times b times a times b times. Yeah, I don't see any difference in writing the A or the B outside. Sorry, I covered it up. I don't see any difference in writing the A and the B outside. In fact, I think it's more standard, frankly, in the biz to write this as x to the A to the B mod y. Or maybe this is saying something slightly different, but in any case, this is the truth. And yeah, that expression there makes sense. It doesn't quite make sense to me. Can you give me like some numbers that hurt your feelings? Like, let's say that we were to do, I don't know, 3 mod 5. Well, we could square this. And I think what you would mean by this is that this is equal to 9 mod 5. No? But of course, 9 mod 5 is equal to lots of different things. I mean, that's the point. And just to show that this is well defined, so this is, by the way, the same as 4 mod 5. Just to show that this is well defined, another thing that you could write this as, you could also write 3 mod 5 equally well as negative 2 mod 5. This is that 3 mod 5 is the same thing as negative 2 mod 5. But notice that if you square this, what do you get? You get 4 mod 5. And oh my God, these are all the same thing. It all makes sense. What does the mod function do? So it's not really a function. Well, kinda. It kinda is. Okay, so here's the idea. I think maybe in Python it's a function. Okay, in Python it's a function. But here's how math folk think about mod something. So let's write down the integers. Negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, etc. Hi, Admiral Stapler. Good to see you. Yeah, percent sign. That's right. So what does like mod 3 look like? What you do is you look at the integers and you divide them, you divvy up the integers into 3 groups. If we're working mod 3, we're going to organize the integers into 3 groups, 3 subsets. And these 3 subsets, well, 2 numbers will be in the same one of these subsets if their difference is divisible by 3. So the most obvious one of these subsets are the numbers which are just themselves divisible by 3. So that's those 3. Now, if you look at, and if I was to include 6 in this list, that would be included, etc. The key thing about these squared numbers here is that if you take the difference of any 2 of them, the difference will again be divisible by 3. That's why these are all in the same subset. Then you can do, you can think about, for example, this subset. 1, negative 2, 4, etc. If you look at the difference of any 2 of these green numbers, the result will be divisible by 3. And if you look at these numbers here in red, again, the difference of any 2 of them will be divisible by 3. And so when mathematicians talk about the integers mod 3, what they think about are, in fact, subsets of the integers. We give a name to these subsets. We call them, well, equivalence classes in one way of speaking. Another way of speaking is cosets. It's another way of saying it. Or differences would be divisible by 5, and there are 5 places apart from one another. Yeah, and the difference, so in any two numbers from a single one of these equivalence classes, the difference between them will always be divisible by 5. So for example, we could write that 16 is equal to 1 mod 3. True. Because what we mean when we say this is that 16 and 1 are in the same equivalence class, mod 3. Now, I think what Python does when it interprets a percent sign b, for example, if we were to do 16 mod 3, I think what it outputs for you are one of these numbers right here. I think this is what Python returns. Because notice that every equivalence class, mod 3, is inside of this green box. I don't know. Does it know what to do with mod negative 3? I don't know. Anyway, modular arithmetic. So, turns out that you can define addition and multiplication operators on these equivalence classes. So we know legitimately how to add and multiply these equivalence classes together. And that's a well-defined operation. Those are both well-defined operations. Meaning that, in fact, what you can do is, like, for example, if you want to multiply, in this case, red with blue, if you want to multiply the red equivalence class with the blue equivalence class, you can take any two representatives of those equivalence classes, multiply those together, and then see what the resulting object, what equivalence class that resulting object is in. So for example, let's multiply a red and a green. And I'm just going to arbitrarily pick -1 as a representative for red and -2 as a representative for green. We're going to multiply them together and we get 2. But if I was to pick some other representative for red and green, like say 4 and 5, these are equally good representatives for red and green, and I multiply them together, what do I get? I get 20. 4 times 5 equals 20. And what's 20 mod 3? Well, it's also red. It's also 2, yeah? 20 is red. That's what I'm trying to say. So that's just one example of the sense in which we have a notion of multiplication of these equivalence classes. And addition is similar. Addition is similar. I mean, we can get deeper with this stuff for sure. We can go deeper and really analyze what we mean by something be equivalent to something else mod n. Happy to do that if that's what you want to see. If that would help you. You want to go deeper on that? Okay. Wait, so I actually don't totally understand what this remainder thing is really all about and why it's weird. Like, is it because of negative numbers or something? Modulo versus modulus? Is that really what it is? What it is? I don't know. What is the remainder operator in Python? So what is the is there a remainder operator in Python? So what would we predict for this guy? I guess 2. This should be 2, right? Which it is. Huh? Do I know the order of operations here? Hi, Love Geo. Yeah, I'm not sure. Does Python have a remainder operator? Oh, this feels like -3 mod 5. Div mod. Wait, that's the quotient, right? Div mod. So that's the quotient and remainder? That's the quotient and remainder. Oh, what the hell is that? Wait, what? Oh, okay. Wait. Oh. No, I don't understand it. So div mod negative 3, 5. So this is saying 5 goes into negative 3, negative 1 times. Which is what's wild, I guess. And has a remainder of 2. But is that not the same as modular arithmetic? I guess what like people were saying in chat, there is a distinction to be made between remainders and modulo. And I'm not sure if Python is recognizing that, or I'm not sure if that's the case in Python. It might be the case in other. It sure seems that way, yeah. So if I do negative 3 mod 5, I'm pretty sure that's 2. And if we do, I guess, negative 3, this one, that's negative 1. I don't know what remainder is. I don't know what remainder is to this machine. No. Negative 3 is equal to 2 mod 5, right? Negative 3 is equal to 2 mod 5. Yeah. Okay. Kappa. Right. All right. Good. Anyway. It is a little spooky to me to say that negative 3 divided by 5 is negative 1 with remainder 2. But maybe it's okay. Maybe it's okay. I just want to know how the x mod y raised to the a is equal to x to the a mod y. It's because when you write x to the a, x to the x mod y raised to the a, you're taking a literal number. I'm gonna use Python conventions here, okay? I'm gonna use Python conventions here. So x mod y returns a number between 0 and y minus 1, which is the result, the remainder of dividing x by y. So you're going to write, so like let's say that, suppose, let me go to a docam. Suppose you do x% y in Python. Suppose that it returns, I don't know, r. Then what this means is that you can write x as some quotient times y plus this r. Right? Now, let's say that you were to raise this x to the 8th power. Raise x to the a. Okay? X to the a is equal to qy plus r raised to the 8th power. Right? And if you know your binomial theorem, then what this ends up being is, well, let's see what we can do with it. It's going to be qy to the 8th power plus n choose 1 qy to the a minus 1st power times r plus n choose 2 qy to the a minus 2 power times r squared. And we keep going all the way until, well, what's the second to last term? It'll be n choose n minus 1 times qy times r to the n minus 1 power. Oh shit, fucking ass, fuck. You're right. I'm only mad because I'm mad at myself. Thank you for the correction. Plus r to the 8th power, right? And now the thing to notice, Connor, thank you so much. Yeah. The thing to notice is you see all this garbage here inside of this blue box. I mean, not blue. Green box. You see all that? All of this is divisible by y. So if we were to take x to the a mod a, x to the a mod y, this entire piece here would go to 0. Or maybe another way of saying it is that because this green box is divisible by y, we can rewrite this whole thing as some big long number k that I don't know the value of, or I don't want to write down, times y. Do you agree? This, I'm just talking about the green box right now. This green box becomes some big ass number k. You see I wrote it with a capital letter, times y. Is that clear? Iconic? And then what we, of course, this is not equal to x to the a. What we can then do is add r to the 8th power. And so what this means is that x to the a is equal to r to the a mod y. So like if you have the equation, what we've shown that if x is equal to r mod y, then x to the a is equal to r to the a mod y. It's about right-angled hyperbolic polyhedra. That's what it's about. It's about so you know boxes, right? Boxes like cereal boxes, for example. So those are examples of right-angled Euclidean polyhedra. The reason they're called right-angled is because the angle between any two faces of the box is a right angle. And it turns out that in a special or different geometry called hyperbolic geometry, you have the analogs of boxes there. And in fact, hyperbolic geometry supports a much richer set of shapes of boxes. Now, they don't really look like boxes. They look like things like more complicated polyhedra, like dodecahedra. So, for example, in a hyperbolic space, there is a right-angled dodecahedron. If you look at this dodecahedron, which is a Euclidean one, you can see that the angle between two faces of this dodecahedron, like let's say these two faces right here, the angle between these two faces is not 90 degrees. It's slightly bigger than that. But in hyperbolic geometry, in fact, there is a right-angled dodecahedron. And so that's what I mean by it sort of being like an analog of a box. And what you can do is use that box in the same way that you can take boxes if you imagined you had infinitely many of them, in the same way that you could fill up Euclidean space. You could tile Euclidean space using boxes. You could tile hyperbolic space using right-angled dodecahedra, or any, for that matter, right-angled polyhedra. So there's an integral also? What do you mean? So I'm puzzled by your use of the word integrating there. But yeah, there are hyperbolic tilings of hyperbolic space by these right-angled hyperbolic polyhedra. These things are of interest to mathematicians. Well, I don't know, to at least some subset of mathematicians, because you can use them to construct what are called hyperbolic three manifolds, examples, like very explicit examples of them. There's, for any hyperbolic polyhedra, right-angled hyperbolic polyhedra, there is an 8-fold manifold cover of it. I'm bad at lying. Like, what I'm not good at playing, like when people play Mafia, like I've played Mafia before. And when I'm that, what do you call it? The murderer or whatever? Or no, Mafia. Sorry, I'm Mafia. I can't do it. It's very difficult for me. I'm not a good liar. Should I get another protect? I think I just do card remove and hi, can I please help you? Find the derivative of 1 over cube root of x to the power 4. So I have medical insurance, yeah, so I don't think they'd charge me, but okay, so let's see. What is the question? 1 over the cube root of x, like this. The whole thing to the 4th power? I just want to be clear on how the problem is presented to you. Yeah, I'm talking to you right now, twee-wee. Do you want me to raise this whole thing to the 4th power or just the denominator? I just want to understand. I know that, like, is the 4 here? Is the 4 here in the denominator, or is it the whole thing? Right, being raised to the 4th power. X to the power of 4, so it's like this. So, yeah, I think it's like this, right? So the first thing to know is that taking the cube root of something is the same as raising that thing to the 1/3 power. That's the first thing to know. So cube root of something like x, this is the same thing, exactly the same thing as x to the 1/3 power. All right. People might quibble, but don't listen to them. This is fine. So I would like to realize this sort of as a power of x ultimately. So the first thing that I'm going to use is exploit this. Now note, this is not calculus that I'm doing right now. This is just pure algebra. So this is rewriting the expression. So this denominator here becomes x to the 4th to the 1/3 power. Is that clear how that happened? The next fact that you want to know is that when you take a power and you raise it to another power, this is equal to x to the product of the powers. Do you have this one, this factoid memorized? Like, so that you feel revulsion when sometimes people will say x squared cubed is x to the 5th? You should feel revulsion. And if you don't, you need to work on that. So are you comfortable with this guy here? Are you there, twee-wee? Okay, so then that means that this is equal to 1 over x to the 4/3 power, right? We multiply the shit together. We get 4/3. Multiply the 4 by the 1/3, get that. Now, some people get weird at this stage, and they say something like, okay, if I ddx this, if I take the derivative of this rather, then I get 1 over 4/3 x to the 1/3. Sometimes people do this. Sometimes people will go, okay, so now I'm going to take the derivative of this, or I'm going to take derivative, and I get 1 over 4/3 x to the 1/3 power. Because they sort of reflexively think that the power rule is applicable to this expression. Or it's like whenever they see an x to the something, they reflexively use the power rule. So don't let that be you, because this is completely wrong. This is completely wrong. But all teachers of calculus have seen this error be made in the past before. The right way to think about this problem is to do a little bit more algebra, which is to write this as a power of just x. Forget about the 1, get rid of the fraction. How can we do that? We can use the fact that 1 over x to the a is equal to x to the negative a power. In other words, we can flip this x to the a into the upstairs, at the cost of a negative sign. So in particular, this algebraic fact tells us that this expression here is equal to x to the negative 4/3. All algebra. This is entirely algebra. No calculus, not even a little bit. In going from here to here, all we've done is rewrite this thing. We've not done any calculus. Now is the time to do calculus, because what we can do is say, aha, that means that the derivative of this, that's the prime there, is equal to the derivative of that. That's a prime there. And now we can straightforwardly use the good old power rule that we all know and love. We bring this number out in front, we get negative 4/3 x, and then we subtract 1 from the exponent. And now this is hard. What's negative 4/3 minus 1? I think it's negative 7/3. Is that right? And you know what that is. That's the answer.
I have an important question.
We're having Discord drama right now. So, Twee-wee, is this good? Do you like it? That's weird. I don't know if anybody else is experiencing that delay. But, well, glad to be of service. Thanks for the question. It was a good one. Oi Jack Sure Takoi. Let D from P4 to P3 be the derivative. Find the matrix rep sub B. Okay. Oh, okay. Yeah, I know. Yeah. This is linear algebra. Yeah. Sorry, my brain is a little offline. All right. Cool. So what we have are two vector spaces and a map between them. We have this map D, which goes from P4 to P3, where P4 is the set of polynomials of degree 4 or less. Polys, and this is, of course, degree 3 or less polynomials. And each of these are given a basis. We're given a basis for P4 called B, which is in order now, 1x, x squared, x cubed, etc. Oh, that's it, rather. And we're given a D for P3, consisting of 1x and x squared. Now, what we want to do is represent. Is P4 not degree 3 or less? Oh, it is? Okay, I guess this didn't. Fuck me. You're right. I like Scuggit. Thank you. You are right and I'm wrong. That's clear from the way these bases are defined. Great. So, we have this setup. And now we want to find the matrix representation of this linear transformation. And I guess what you're calling that is rep sub B D of D. And the point is that what this is going to be is a map not from P4 to P3, but rather from R4 to R3. which in some sense represents precisely what this linear transformation does. Good. So what we're going to do is we are going to, so to figure out what the matrix here is, this is going to be a 3 by 4 matrix, I believe, because we're going from R4 to R3. It's going to be a 3 by 4 matrix. Let me write that. What we do is we're going to apply D to each of the basis vectors and then see what the resulting coordinate vector of the result is in R3 with respect to this basis. And then that will be the that will represent the various columns of our matrix. Is that clear? Oi Jack Sure Takoi. Okay, so then first, let's take the first basis element of B. Apply D to it. What do we get in P3? Applying D to 1. Is it me that's lagged? No, we don't. What's the derivative of 1? I know you know this. What's the derivative of 1? It's 0. That's right. So in other words, via D, 1 goes to 0 in P3. Now, how do we represent the polynomial 0 in P3? How do we represent that as a linear combination of these basis vectors? Like, in other words, what are the coefficients of that of those the coefficients that sit in front of these 3 polynomials that gives us the 0 polynomial? They're all going to be 0. That's right. So you know what the first column of this matrix is going to be? It's going to be 0, 0, 0. These zeros, what are they? They are the coefficients of 1x and x squared. And what is 0 times 1 plus 0 times x plus 0 times x squared? Well, it's the 0 polynomial. And why are we looking at the 0 polynomial? Because that is the image of 1 under D. Did all of that make sense? There are a lot of things happening there. But this is how it's done. All right, now you do the same game, but now we start with, instead of 1, we start with the next basis vector. So what's d dx of x? Excuse me, what is d of x? It's 1. And how do we express that as a linear combination of 1x and x squared? Don't think very hard, please. We're going to take, I'm going to tell you, I know you know, we're going to take one of those, 0 of those, and 0 of those, right? 1, 0, 0. I don't know why I did that. If only I had an iPad Pro, then I wouldn't have to do this. Okay. Next one, x squared. But I don't get the iPad Pro. I get this fucking thing. My wife gets the iPad Pro. 2x. What column vector do I write then? You're right. What column vector do I write? 0, 2, 0. Hype. You're totally getting this. And what's the last one? What's the last column? It's true. Does she have 33 people watching her while she's doodling on the iPad? No. Oh, careful, please. Oh, careful. D of x cubed, what is it? I know you know. Yes. And there it is. No, don't apologize. There it is. Okay? And the point of this matrix now is that if you take an arbitrary polynomial here in P4, like let's say we are interested in the polynomial 4x cubed plus 2x, say. Okay? Then what we can do is we can represent this as a coordinate vector. This thing is a coordinate vector, has a coordinate vector with respect to the basis B. And that coordinate vector is 0, 2, 0, 4. You agree? And now this vector here, this polynomial, if we apply the map D to it, what do we get? Well, this is Calc 1. We get 12x squared plus 2. And this has a coordinate vector with respect to the basis D. Its coordinate vector, so maybe can I denote things like this? This coordinate vector is, well, it's 2 for that 2 there, 0, and 12. So the coordinate vector of the output of D is 2, 0, 12. The coordinate vector of the input to D was 0, 2, 0, 4. Now, here's the magical thing. If we take this matrix here that we just computed and we hit this vector on the left by this matrix. So in other words, we compute 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, and we multiply this by 0, 2, 0, 4. What do we get? Well, we get 0 plus 2 plus 0 plus 0, so we get 2. We get 0, 0, 0, 0, and we get 0, 0, 0, 12. Huh. 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 All right. That's the point of this. Is that you transform this linear transformation into matrix multiplication. You're so welcome. Thank you for the good question. I appreciate it. If anybody else has a question out there, you can type !join and maybe I can help you. That's okay, Twee-wee. I am a patient man, or at least that's what I would like to believe about myself. Self-image, the image of self is important. And in my image of myself, I am a patient man. Yeah, sure. Hey, asked you a question. Go Democrats. Have you a question? I heard that the Senate is, there's like a really good chance that we get that the Democrats get the Senate in November. That's what Nate Silver said to me through his website. I might actually go into crescendo here. Later, QST. Thanks for hanging out. Oh my god, and thank you for all those subs. That was so nice of you. Really nice. Which one is the Senate? The Senate is 1/2 of the Congress. Congress is what's called the legislative branch of our government. It's like the equivalent of like the Parliament, maybe, in Britain. And the Congress splits into two halves. There's the House of Representatives and there's the Congress. Sorry. The Congress splits in two halves. There's the House of Representatives and there's the Senate. Okay. The House of Representatives has representatives from each state, which is a number of representatives from each state, which is a function of the state's population, a monotonic function, hopefully, of the state's population. So the more people that you have in your state, the greater the representation is in the House. So here are some famous House of Representative members. There's Nancy Pelosi, who is the Speaker of the House. Second in line to become president. It should something tragic happen to our dear President Trump. If Trump goes down for some reason, like is incapacitated in some way, our vice president, of course, is the first to step up. But then after the vice president is Speaker Nancy Pelosi. Then, so she's famous. There's also a famous person named Alexandria Ocasio-Cortez, Twitter goddess, queen of the progressives, or at least the not too far gone progressives, the ones with some sanity. Anyway, yeah. So there's her. Trying to think of some famous reps who are Republicans. I don't know. Forgot. I don't know who any of those people are. Anyway, then there's the Senate. And the Senate, each state gets 2 senators, regardless of population. Yeah. So right now, for example, in my state, California, we have a long-serving senator named Dianne Feinstein. She's been in the Senate for representing California for a very, very long time. And I believe our other senator right now is Kamala Harris, who is currently running with Joe Biden to become on the Democratic ticket for the president, to win presidency. She's his vice presidential running mate. Other famous people: Mitch McConnell, who I think is from Kentucky, who is a very famous Republican obstructionist. I don't know. I'm not sure if she was on the Senate Judiciary Committee. I'm not sure. Okay. I didn't watch any of it. I thought it was more or less a foregone conclusion. Also, you may have heard of Ted Cruz. He was a Republican nominee. Amy Klobuchar is also a senator, right? I disavow white supremacy. So easy. Yeah, so that's Congress. We have two other branches of government as well. We have the executive branch and we have the judicial branch. And the significance of the Democrats winning the Senate is that if they have any spine, it's not clear that they do, but if they have any spine, they could conceivably, quote unquote, pack the courts. Right now, the courts, the Supreme Court has a 6-3 split ideologically. 6 of the members are conservatives. 3 of the members are more progressive. So this does not bode well for various laws or findings that the Supreme Court had previously upheld. So one of those, for example, is basically access to abortion. It's this very landmark decision called Roe v. Wade here in the United States. And a lot of people feel that although maybe there will be certain states that will be okay in this, if Roe v. Wade should get overturned by the Supreme Court, and there are attempts to overturn it all the time, that this will, in some states, remove the access of legal abortion to many, many women in these states. And now that Amy Coney Barrett, is that her name? Now that she's a Supreme Court justice, I don't know. It seems like Roe v. Wade will probably go down. You want yeah, sure, linear algebra, go for it. Have I tried the blue-eyed black-eyed islander problem before? No. It does suck. You know, Ruth Bader Ginsburg, it was like, you know, she was trying to stick it out, but she had like pancreatic cancer. I think that's what it was. And she was dealing with that for like a couple years, I think. And that's like the deadliest cancer that there is, I think. Or I mean, maybe there's some rare one, but that's worse. But and you don't want a rare cancer because that means that nobody's gonna develop any drugs for it because there's no profit in doing so. But she had pancreatic cancer, I believe. Yeah, not good. I had a blood cancer, which is luckily a very well-researched thing. Like leukemia, lymphoma, these are blood cancers. And so I had very good sort of modern treatments, I guess. Top-of-the-line treatments. You know those things, the monoclonal antibodies that are used in remdesivir, this new COVID-19 thing? Well, I had a monoclonal antibody called Rituxan as part of my frontline treatment for lymphoma. These things are developed in genetic labs, and they take, antibodies that of course they do shit to the mice, and then they harvest their antibodies and put them in a plastic bag, sell them for $15,000. Oh, yeah, I'm bringing it down for sure. All this cancer talk, but I'm also fascinated by it. Yeah. Cancer is a fucker. Okay. Let V be a vector space. I said vector. I did say it. It did happen. Let V be a vector space with basis B, beta 1 through beta n. Beta 1 through beta n. And let G be a homomorphism. Suppose that there are numbers, real numbers, such that da da da. Ooh, yeah. What is rep B, B, G? How did you know that, Vectorcom? Are you a biotech person? Yeah, it was a huge step forward in the treatment of non-Hodgkin's lymphoma after a period of serious stagnation. Like, I kind of think like right now we're sort of in the golden age of biology. Like things, oh my God, what? That's incredible. Yeah, we're sort of like in this golden age of biology, and you know, it's biology and machine learning, okay, and maybe the intersection between these things. I don't know, but yeah, like the power that we're having over the genome and stuff like that is like unprecedented. Almost certainly, yeah, almost certainly. Mathematical biology is, yeah, big deal. Biomathematics. There's also bioengineering, which I would imagine is exploding. Bioinformatics, sure. Oh, sorry. OIJAC. Like, physics, I love you, but I think that the golden age of physics has passed. We're on to newer things now. Probably now with alongside the information revolution, we're seeing a parallel trend in sort of biology. That's sort of my sense of humanity right now. Of course, never mind. Let V be a vector space. So what we have is this homomorphism G, which runs from V to V. We have bases, or a basis B, consisting of beta 1, beta 2, all the way up to beta n. Look at these long, beautiful tails on my beta. And then we have that G of B1, or really G of BI, I can write. So when we take, G of BI, this is equal to lambda I times beta I. Oh, this is a B. I messed up. That's actually a beta. My bad. Imagine that. I get betas looking things and capital B's mixed up. It happens often. Now we want to know how to represent this using a matrix. So this is very important, OIJAC. You will learn this in your not so just peanut chill. You will learn this in the not so distant future. You're gonna learn that this condition means, this is the word that we use, that beta I are eigenvectors of G with eigenvalues lambda I. Anyway, I think what you're going to notice then is that no, not scary. I know it sounds scary because German, right? Eigen sounds like frightening. And as a red-blooded American, which I'm guessing that you are, you understand. But in fact, eigenvectors and eigenvalues, yeah, totally cool. And they're super useful, all right? So don't be scared. Anyway, so now we want to represent this matrix with respect to this we want to represent this linear transformation with respect to this basis here. Here's my first question. So we have to follow the process that, roughly speaking, we did in the previous exercise. In that exercise, we were able to obtain the columns of the matrix by applying the linear transformation D to each of the basis vectors in turn. For example, applying D to 1 got us the first column. Applying D to X got us the second column. Applying D to the third X squared gave us the third column, etc. So now suppose that we apply G to the first basis vector. Well, what do we get? Well, we're told we get we get lambda 1 beta 1. Are you following me, Ojak? Actually, with a name like Ojak, it's probably Australian. Oi, right? Oi, mate. Oi, mate. Oi, mate. Yeah, so... Oh, you're from Nepal. I was way off. Okay. Sorry. I don't know why I thought you were from America. No idea. So G of beta I is equal to lambda I beta I. Okay. It's just American chauvinism. That's what it is. Pure and simple. I'm an American, by the way. So G of beta I is equal to lambda. Oh, see? I nailed it. Never mind. It's not American chauvinism. It's just American, good old American gut intuition. G of beta I is equal to lambda I beta I. So in particular, G of beta 1 is equal to lambda 1 beta 1. So now how can we express lambda 1 beta 1 as a linear combination of these basis vectors? Like, what are the coefficients that we're going to use to express lambda 1 beta 1 as a linear combo of these things here? Yes. Yes. So the first column of your matrix is going to be lambda 1 and then zeros all the way down, right? The second one is going to have a 0 here, then a lambda 2, then zeros all the way down. And probably you can guess what will happen. For example, the last column will be all zeros, and the last entry will be lambda n. The only entries which could be possibly non-zero here are the diagonal entries. And the diagonal entries are precisely these lambdas. Hold on. An alarm is going off at port 5. Kill it. Anyway. We happy now? Well, first of all, I want you to notice this is an extremely nice matrix. Do you agree? Diagonal matrices are ridiculously useful. They're ridiculously nice to work with. For example, try multiplying something by a diagonal matrix. Put something over here. Do a diagonal matrix times something over here. You will see that the diagonal matrix multiplication is so much more simple, so much simpler than full-on matrix multiplication. You will see that, okay? And so in particular, note that it is precisely this eigenvalue, this eigenvector condition thing that I mentioned before that allows you to have one of these diagonal matrices in your midst. Now, it may not feel significant right now, but like just in terms of applications, if you have like 1,000 by 1,000 matrix or something like that, and and you can make all of the entries except for the 1,000 along the main diagonal be 0, you are going to save yourself a shitload of computation if you ever have to work with that matrix in any serious way. Do you see what I'm saying? Because instead of having to deal with 1,000 by 1,000 matrix is going to have 1 million entries in it. And multiplying, using that matrix to multiply something by is going to require, perhaps some really, really serious computation, which is why diagonal matrices are so lovely to work with. They cut down on the computation that's required. And maybe you think, oh, I don't give a shit. Well, okay, I'm with you. I don't really worry about 1,000 by 1,000 matrices. But lots of people do. Lots of people do. And so being able to find nice columns for matrices by using eigenvectors seems like a nice little thing. They have importance in mathematics, within mathematics. They are they represent sort of invariant subspace they're just really important. Like for example, here's a good one. Like when you're those video games with computer graphics and stuff. You can understand rotations and things like that using eigenvectors and eigenvalues. Oh, that's good for your physics professor because of course they arise in physics. In fact, they arise in a really essential way in like quantum mechanics. Hey, I need a new graphics card. Hey, should I wait for the AMD cards? Is that how that works? Like I heard the AMD ones are better. Oh, okay. I'm not going to spend that much money though, but maybe I'll wait for them to come out and then see if prices drop. I don't play very fancy things. I just want to play Slay the Spire. Can I do that? I'm not even sure why I need a new one, frankly. I don't know, because it feels old, that's why. Isn't that a dumb reason? Well, it's like I feel like right now, with now that I'm doing streaming, like maybe things are chugging just a little bit. Like things, I don't know if it's my video card, but things are like, like I can't move this window very fluidly, the OBS window. In fact, I'm a little scared it's gonna crash. So I feel like that's a symptom of my GPU, but I don't really understand anything. Like I've got a pretty good processor. I've got a pretty good set of RAMs. It's a good set of RAMs that I have. So let's see. What is my thing? I have AMD Ryzen 5 2600. That's my thing. And I have NVIDIA GTX 660. That's what I have. And I have a where does it say my memories? I have 16 gigs of memory of RAMs. Why are people laughing at me? What? I'm not sure what's going on. But the oldest part of this computer is this graphics card. So I thought it was kind of if I wanted to make things better on my computer. I have no fucking idea what that means. Yeah, that's what I have. GTX 660. What is so goddamn funny? I don't get it. You're gonna have to explain yourself. Okay, never mind. I don't care anymore, alright? What? Whatever. Alright. Yeah. So I figured like the graphics card was not so great. Also, I'm not sure about the state of oh, okay, cool. Yeah, I can wait. It's not a big deal. Oh, look, it's Devil Honor. Let's go. Devil Honor's got a question. We always like Devil Honor questions. You're having your doubts, are you? What are your goals in life? What's important to you? There's no wrong answer. Are you becoming disillusioned with math? Remind me. You're maybe a second or third year math major? I'm just guessing. Second year. Hi, Cootie Juice. I'm not judging here. But if you're saying that Wiles ain't getting that the good stuff, I don't know where you're coming from. Math. So where you are right now, Devil Honor, math just gets more and more interesting. It really does. Okay? And if you're good at it, you can make a life out of it. Okay? In other words, you can become a mathematician. You can. Now, I will say this, rather. Math is very, very difficult. It's hard as fuck. Okay? We have to acknowledge this fact. I think, personally, it entails quite a bit of suffering. Straight suffering. And very difficult. It's difficult. It's very hard. Those rigors are made, I mean, that's just the material itself. Then if you want to actually get a job doing math, well, that's a whole nother challenge in and of itself. Now, if you, for example, get through somehow, and you get yourself a PhD, or, I mean, even I would say probably an undergraduate degree in math. I mean, I don't need to be thinking that far ahead, maybe. If you get yourself an undergraduate degree in math, there's likely a very good chance that it seems like you're eminently employable to me anyway. You're employable. So if your goal is to get a job and make big old bank, you know, that kind of stuff, a math degree isn't a bad place to start in that project. Maybe learn some programming to make yourself more employable. It really depends on your interests. And it's hard to say for somebody. That's no. I knew some dudes in grad school, very strong mathematicians, had some very funny eating habits though. Like, I think one guy was super into just eating the same hamburger. I'm not sure how many times a day, but just eating hamburgers basically all the time. Yeah, talent is listen. There are people that have been studying math their whole life. Not only that, these people are also incredibly smart. And they have, I mean, I don't know what your history is, Devil Honor, but if it's anything like mine, many years of your youth were wasted on bad education, bad schooling, and a lack of, just a general ignorance within the close circle of friends that you have and family around you about what math kind of looks like. This is an unfortunate situation, but it is the reality. It was for me anyway. And although I did well as an undergraduate, when I got into grad school, I really acutely felt the differences there. And I felt like pretty demoralized, if I'm going to be absolutely honest, because I could see these people were operating on levels of sophistication. They still are operating on levels of sophistication which far exceeded my own. And that was, I have to be honest, it was demoralizing. But it was, if I got over that, right? Or at least to some extent I got over that. And I just did my own thing. I tried really hard. I worked hard, and I was eventually successful. Yeah, I'm with you there, Devil Honor. But you know what? You know what can make up for all of that kind of stuff? Seriously, is hard work. Like, hard work is really, really valuable. A lot of people don't have that kind of work ethic. Now, some people do, okay? And some people have been doing this their whole life. Those people are scary, but you can't compare yourself to them. What matters is that you get a little bit stronger every day. If you get a little bit stronger every day, then you are way ahead of a lot of people. I have exactly the same regrets, though. I just haven't clicked your name yet. I have to click it. I'm done talking about this. No, Devil Honor, do not compare yourself to others. Do your own thing. Focus on your studies. Get stronger every day. Self-improvement is where it's at. And if you can maintain that, then you will find yourself surpassing other people. What does the push forward of a sheaf mean? So presumably what it means, let me think for a moment. See, I would think that it would be more common to talk about the pullback of a sheaf. Let me think for. So if we have a continuous map, let's say from x to y, and this is what I imagine it refers to, and we have a sheaf over here, E, then I would expect there to be an E prime over here. This is what how I would interpret a push forward. I guess we could just pull back, maybe. Look at the fiber over, or what do you call that? The thing over that over the open set here. So if you have an open set here, U in Y, right? Wait, what? So what Wikipedia is saying is that if you have open set U in Y, say, then the set that lives above it, you can obtain from this data. If we call this thing here F, we call this thing here small f. The set that lives above the open set U here in Y is, you call it F star F of u. So this is supposed to be the push forward of the sheaf on x. You define this as f of f inverse of u. So this thing here is our f star of f. F star f. I guess that makes sense, huh? So basically, to open sets in Y, you first, to define the set above that open set, the image of this set under this functor, you pull it back to X using the continuous map F. That the function is continuous means that F inverse of U is an open set in big X. You look at the associated set via the functor F, the sheaf F, and you define that to be that image. You define that to be f star of f, the push forward sheaf at U. I guess that makes sense. 1, 1, 1, 0, 1, 1, 0, 0, 1. So if that's the matrix, then we should be able to, for example, so like under this map that you've got here, where does 1 go? What is h of the polynomial 1? Can you tell me that? Sorry, let's go back to the doc. What is h of 1? Oof. What is a, b, and c for 1? What are the values of a, b, and c for this polynomial? So for this guy right here, what's a, and what's b, and what's c? No. Okay, so we're given a formula. We're told that h of a plus bx plus cx squared is equal to a plus b plus b plus cx plus c plus a x squared, right? So I'm asking you, what's a, what's b, and what's c? I need to know that so that I can compute h of 1. So if our polynomial is 1, what's a, b, and c? This is not a hard question, not a trick question or anything like that. What's a, b, and c? Yes. 1, 0, 0, right? So now what is h of 1? Well, we do a plus b, which is 1, because a is 0. Sorry, a is 1, b is 0. We do b plus c, but notice b plus c is 0, so I'm not going to write anything because that's insane. Plus a plus c, which is 1. So h of 1 is 1 plus x squared. You agree? Now, remember, what is our basis b? Our basis b is 1, 1 plus x, and 1 plus x squared. So what we've successfully done is compute h of 1. And we found that it's 1 plus x squared. But now what we need to do is we need to express this polynomial as a linear combination of these three polynomials. So in other words, we need to be able to say that this is equal to, I don't want to use A. We want to find numbers. What are some good numbers? P1 times, so that 1 plus x squared is equal to P1 times 1. Where did that 1 come from? 1 is the first basis vector, plus P2 times 1 plus x squared, plus P3 times 1 plus x squared. We want to find P1, P2, and P3, which will make this polynomial here equal to 1 plus x squared. Are you following me? Oh, I messed up. Yeah, I made a typo. Thank you. P3 is 1. P3 is 1. P2 is negative 1. And P1 is 1. Is that what you're saying? Yeah, good. So we have, I think that's correct. 1, negative 1, and 1. Nice. So what's the first column of our matrix going to be? This implies the first column of the matrix is 1, negative 1. 1, negative 1, 1, rather. That's the first column of our matrix. Now what's the next step? The next step is to do the same process, but now to 1 plus x, the next basis vector. Does that make sense? Okay. And what I'm hoping is you can do this. Can you do this? It's okay if you say no, but just let me know. Do you feel comfortable venturing out on trying to do this on your own? All right. Does anybody else have a question about anything? Hello, Halotron. I wonder why it didn't pick up in my streamlines. Well, just go ahead and ask your question, Halotron. I'm not sure why it didn't show up in my handy dandy list here. What, you're supposed to solve that equation, Halotron? Uh-oh. So this is going to require that I know something about trig stuff. But I think this is doable. Okay, so let's see. Sine of x. Oh, you need to see this. Sine of x over 2. You still can't see it. Sine of x over 2 plus cosine x minus 1 equals 0. So sure would be nice if we could rewrite this in terms of cosine. It's annoying, or in particular, if it would be nice if I could rewrite this using as cosine of x something. And I think that there is a tool to do this. I think there is a tool, don't quite remember it, but here's what I do know. Let's see if we can use this fact. Oh, do you know the half angle formula off the top of your head? Because I don't. That's my problem. I was going to derive it. Darn. What? Radicals? So here's what I know. I know that cosine of x, so in general, cosine of, let me say a plus b is equal to cosine of a cosine of b minus sine a sine b. I know this. So this means that cosine of 2a, if I make a equal to b here, then cosine of 2a is equal to cosine squared of a minus sine squared of a. And I can rewrite the sine squared of a using good old Pythagoras. So this is equal to cosine squared of a minus 1 minus cosine squared of a, right? This minus touches the 1 and it touches the cosine minus cosine squared, and what I get is 2 cosine squared a. Yeah, I shouldn't have been attacking sine or cosine of 2a. I think I should be attacking sine of 2a. So is there a formula out there for sine of 2a 2 over x over 2 rather? You know what? I'm just gonna look it up. I don't want to think about it. Half angle identities. Sub u equal x over 2? Why? It will? Okay, so if I let, I believe you. Let u equal x over 2. So we're just going to define a new thing. And what we get is sine of u plus cosine of 2u minus 1 equals 0. And then it's too late. The train is rolling. It's moving out of the station. And then the point is that this cosine 2u, we can use, we can use the shit I erased here. Because, okay, shoot. Let's go back. So we had this line right here. I'm going to rewrite it, okay? We had cosine of 2a being equal to cosine squared a minus sine squared a. So now notice the resemblance between these two expressions. Sure, it would be nice if we could rewrite this totally in terms of sine, which we can do. And the reason is because cosine squared of a, we can rewrite using Pythagoras. This is equal to 1 minus sine squared of a minus sine squared of a. And of course, that simplified is 1 minus 2 sine squared of a. So now let's apply this to that. Deal with it, okay? Sine of u plus 1 minus 2 sine squared of u minus 1 equals 0. And now look. Those things die. So then we learn that sine of u minus 2 sine squared of u is equal to 0, which means that if we factor out a sine of u, we get this. And so either sine of u is 0 or this other factor is 0. Now, when is sine of u 0? So let's see. What did you say? You gave me bounds on x. You said x had to be between 0 and pi or 0 and 2 pi? 0 and 2 pi. So if x is between 0 and 2 pi, then u is clearly between 0 and pi, right? Because as x goes from 0 to 2 pi here, u goes from 0, well, to pi. 2 pi over 2 is pi. So you want to find all values of u which is for which either sine of u is 0 or 1 minus 2 sine of u is 0 in this interval from 0 to pi. Okay? And those are both easy. So for example, when is sine of u 0? Well, the only time that it's equal to 0 in this interval is 0. This implies u is equal to 0. So that's one solution. The other solution, if we just manipulate this a little bit, we add 2 sine u to both sides, divide by 1/2. What we need out of this equation is that sine of u be 1/2. And when is sine of u 1/2 in this interval? Well, that actually happens at 2 places, right? There are 2 values of u which will have a sine of 1/2. Those will be this one and that one. Pi over 6 and 5 pi over 6. Of course, these are solutions in u, and what you need is solutions in x. So what you do is you plug these values back into here and solve for x, and then you win. Okay? Math train. Saint of Doom X. What up? How about after Saint of Doom X goes, okay? am tired. It is true. I don't know why. I think maybe I'm having like allergies, maybe. I'm not sure. I wasn't tired this morning, though. A geometric interpretation of trace. So my immediate go-to is to say that it is the sum of the eigenvalues, which is a true statement. I don't know that I have a geometric picture of what that trace sort of represents in terms of the linear transformation. I don't know. Does anybody else have any input on that question? Sorry. Oh, if you have a projection matrix, then the trace is the dimension of the image of that matrix. Yeah, idempotents. That's right. And idempotents are going to have eigenvalues 1 or 0. Yeah, my head is swimming a little bit. Yeah, sorry. I'm not sure how to interpret the trace for a general thing. That's for sure. Idempotence, yeah. If a squared is a, then yeah, the eigenvalues are always 1 or 0. I mean, like a lot of these things are, I mean, by virtue of the fact that the trace is the sum of the eigenvalues, right? This thing is going to arise as a sort of invariant of the matrix, right? A sort of something that's independent of the basis chosen. So, in that sense, it's intrinsically useful. It's like some kind of intrinsic thing to the linear transformation. Yeah. Oh, we've been hovering around 30-ish viewers, I think, something like that. It's kind of wild. Maybe I'll go back to science and math, or science and tech. We'll see what happens. I'm probably going to log off soon anyway. But what's up, Halotron? Why? I don't know what your formula is to begin with. What is up with these cards? They're so expensive. Gross. Rate of change of volume interpretation? Really? It looks plausible. Yeah. That looks plausible. It's also making me want to puke. But I would guess that what you could do to fix that thing up is you could so replace this by plus or minus square root of 1 minus cosine x over 2. Oh, you can't see. And then move this garbage over to the other side. So you get 1 minus cosine of x. And then what I would suggest that you do is that you square both sides. Now, when you square both sides, you need to be very careful because you could introduce new roots, new solutions, because squaring is not a reversible process. But if you do square this, what you get is 1 minus cosine of x on this side over 2 is equal to, and you can do this, 1 minus cosine of x, this whole thing squared. And again, what you get is a quadratic in cosine. Oh, I guess up on the other side we got a quadratic in sine. Oh yeah, that's a good point. Yeah, that's a good point. It's quadratic in 1 minus cosine of x. Yeah. But then this should be doable from here. Okay. Oi Jack, sure to koi. What's up? Oh yeah. Yeah, no sweat. Thanks for the question. Oi, Jack, you out there? Fond of my options here. My God, how many of these problems do you have? Okay, so again, it's the same idea. You're going to apply f to each of the basis vectors and then see how see what the output is, see what those outputs, how they are represented with respect to the basis D. Don't apologize. So here we have B equal to the basis 1, 1, 1, 0, 1, 1, and 0, 1, 0, 0, 1. And then we have D, a basis for R2, given by 1, 3, and 0, negative 1. And of course, what we have is is f of, I would imagine, A, B, C. Oh, okay, fine. There, okay, fine. Shit. I see. These are not, these should not be written as columns. These should not be written as columns. Instead, what you should do is write B in rows, just like what you said. So B is equal to 1, 1, 1, 0, 1, 1, and 0, 0, 1. We're reserving columns for the coordinate vectors. D is the set consisting of 1, 3, and 0, negative 1. All right, and then we have F. It eats an A, B, C, and it spits out a 3A plus B, comma, a 2B minus C. So now what we want to do is apply F to each of these three basis vectors in turn. Let's just do one. Okay, let's apply F to 1, 1, 1. F of 1, 1, 1 is, as per this formula, 3 times 1 plus 1, which I think is 4, and then 2 times 1 minus 1, which is 1. Do you like it? And now your job is to figure out, how is this a linear combination of the elements of D? And I think it's relatively easy to see that this is going to be 4 times the first vector, right? We get 12 now, and we want to subtract off 11 of that 12. So we're going to use 11 of copies of this guy. So then the first column of the matrix is, well, we get that from these numbers right here. It's 4, 11. And now you repeat this process for each of the other basis vectors. And this will give you the second and third column. Does that make sense? Yeah, representation theory is a little bit niche. No, don't apologize, please. It's good that you're getting practice. Here's what I think your question is. How do I find... So, like, here we are able to find these coefficients more or less by using our eyeballs. You might ask, how could I find these coefficients more generally? Right? If I'm given some random ass vector here, which occurs as the output of f, if I'm given some random pair of numbers, how can I figure out what these values in the box are? Do you think that that's a good question, or do you think it's not a good question? Or do you think that question is relevant to you or not? Do I think numbers are real? Yeah, you know what? I don't give a shit. I don't know if they're real. Furthermore, I don't give a shit. If they're not real, doesn't matter to me. I have a feeling they probably are real, but yeah. Nothing in my life will change. Nothing in my life is affected by whether or not real numbers are in fact real or not. I kind of think like that whole thing is weird because it feels like at a certain point maybe, well, never mind. Ontology is. Yeah, exactly. You can just do linear algebra. Yeah. That's exactly right, Oyjak. So good. I think you get it. I just think maybe in execution, it's coming out a little bit off, perhaps. I don't know. Pop off soon because got a headache behind the balls of my eyeballs. You see the eyeball, there's eyeballs here, and then there's the region behind it, and there is headache content back there. I think I have to take Wish Plus. This is a pretty fucking great card. And let's see what our thingers are. This is shit. That's not... I think it's this one. All right. I've been working on this run for 30 hours. I think I left it open all night once. All right. I'm going to save here because I have headache content behind my eyeballs. But hey, ooh, that light is bright. Hello. It's been fun here tonight. I had a good time. We talked about a lot of stuff. Golly, a lot of stuff, didn't we, today? And I went a little bit longer than I usually do, but that's okay. Let's go visit the Dino Chad, man.
Take care.
Let's raid Paleontologizing.
Thank you for
I hope to see you all in a future stream. I'll do this again tomorrow. Yeah? Until then, I love you. See you. Peace out. All that kind of good stuff. Say hi to Dino Chad.